Hey there, welcome back to 2241. This is the 2.2 examples video on arc length and curvature. So here, we're going to start working on some arc length problems. So find the length of the section of a unit helix in one rotation. All right, so what does a unit helix look like? I have to give you the parameterization for this. The unit helix is given by these equations. Actually, these functions, not equations. Maybe you can think of them as parametric equations. Okay, so here's our unit helix parameterization. And we want the length of the section of a unit helix in one rotation. All right, so let's see. I want one rotation, which is 0 to 2 pi, and I want the norm of the derivative to be plugged in there. All right, so I need my derivative. This is going to be minus sine, cosine, and then the derivative of t is just 1. So now we can compute the norm of this vector. And what do we get? Note the norm can depend on t. Square root of sine squared plus cosine squared plus 1. And sine squared plus cosine squared is equal to 1. So this is really just the square root of 2. All right, well, that makes our integral very easy to compute. We just have that this is equal to integral 0 to 2 pi of the square root of 2 dt. And that should give us 2 pi times the square root of 2. And so that is the length of one section of a unit helix. So if you go from here around and then back to here, this has length 2 pi times the square root of 2. Okay. So now, given the helix as before, we want to reparameterize it in terms of arc length measured from 1, 0, 0. Okay, so this is just arc length measured from, well, 1, 0, 0 is achieved when t equals 0. Sine of 0, 0, t equals 0, cosine of 0 is 1. That's that point. Okay, so 1, 0, 0 means start with t equals 0. And then we have to write down our arc length functional. And this is 0 up to t. Note t is the variable in the upper bound of the integral. Might have seen this in the fundamental theorem of calculus part 1 problems in Calc 2. And then we know that our norm of the derivative vector is still just root 2. So if we integrate this, we should get square root of 2 times t. Okay, and then there's our relationship. So s is equal to the square root of 2 times t. All right, well, if I solve this for t now, then t equals s over the square root of 2. And that can go right back into my parameterization. So now I can write r as a function of s by finding every t in those parametric equations and replacing it with s over root 2. So cosine of s over root 2, sine of s over root 2, comma, s over root 2. There we go. All right. And this is a reparameterization. We've simply written t as a function of another variable, in this case, a very special variable, and then replaced it in the vector function. Right. Now we're going to compute some curvature. So show that the curvature of a circle of radius r is the inverse of the radius. All right, so how do I do this? Well, first off, I need some equations for a circle. So I know a circle is given by x squared plus y squared, and then the radius is capital R squared. And you say, all right, well, it says any circle. It doesn't matter where the circle is placed, so we might as well use the one at the origin to make our lives slightly easier. All right, so now we need some parametric equations for the circle. Those are going to be given by our standard one, which is our standard ones. We might as well make this a two-dimensional vector. Save ourselves some trouble. And we've got cosine of t, sine of t. Okay. Now our curvature is the norm of the derivative of the tangent vector. So we can do this in a couple of different ways, but if we're just using those formulas directly, we need this. Okay, so that means that we need t, and we need it written in terms of s. All right. The other thing that we can do is rewrite this as norm of dt with respect to t divide by ds dt. And this is convenient because ds dt is just the norm of r prime. And that comes from our arc length function formula. So if we come back over here, this thing was norm of r prime. Our first fundamental theorem of calculus says you take the derivative of this and you just put the variable t in here. So you get norm of r prime as the derivative of s. All right, so let's go ahead and start computing some stuff. We'll need r prime. This is negative sine of t cosine of t. Our tangent vector is going to be that divided by the norm. Oh, and actually I used the wrong parameterization here. That needs to be r cosine of t and r sine of t. I need to make sure that I'm taking the radius into account here. So let's fix this real quick. Minus r sine of t and r cosine of t. All right, then our norm is going to be the square root of r squared, so just r. Okay, that makes plenty of sense, hopefully. And then our tangent vector is this divided by the r right there. Okay, so that tells me that t of t is minus sine of t cosine of t. All right, now I need the derivative of that and to take its norm. So t prime gives me minus cosine of t minus sine of t. And lastly, I'll need the norm of that. You can probably see that this is going to be 1. And so that part is 1 for us. This part is r, and we have exactly the formula that we want. The curvature of the circle at any point is 1 over r. And this makes sense if you're thinking of the osculating circle. So the osculating circle for a circle at any point is itself. All right. Next, we want to find the curvature function for the twisted cubic. I never gave you parametric equations for it, but this is what they are. And I want to find the curvature of this curve at 0, 0, 0 at the origin. So given these equations, we have that 0, 0, 0 corresponds to t equals 0. So again, we look at this in the equations and try to find a value of t that outputs that vector. And now I want the curvature for this guy. All right, well, now it might be useful to use the other formula for curvature. So let's write that down. Curvature is right here. Curvature as a function of t is the norm of r prime cross r double prime divide by the norm of r prime cubed. So the cube is important there. Now this formula can be written a different way. It's going to be easier in this case for us to just compute it as is, but I'd like to at least write that formula out real quick. So we have the norm of a cross product, and if you remember, that can be rewritten as the norm of the two vectors times the sine of the angle between them. And then Theseus, quiet. Quiet. 3, 2, 1. And then divide by r prime cubed. All right, and then so sine theta here, this might be a little bit annoying because I don't know what that angle is. But remember that I can find the cosine of the angle between two vectors by computing their dot product, not r and r prime and r double prime, divide by their norms. So we're going to get some simplification. All right, and that's the cosine. So then the sine, if I draw a little triangle here, here's theta. And if I call this top part A for adjacent and the bottom part H, then I have A, H, and this is the square root of H squared minus A squared using the Pythagorean theorem. So that then tells me that the sine of theta is the opposite over the hypotenuse. This is O. And so we have square root of H squared minus A squared divided by H. All right. H was the product of those two norms. And so we can simplify this formula a little bit to norm r prime, r double prime, divide by norm r prime cubed times square root. Now H is the product of the norms. So we have r prime squared, r double prime squared, minus A, which was the dot product, squared. We have r prime dot r double prime squared, and then divide by the product of the norms. And this now gives us some cancellation here. So those guys cancel out there. and we're left with an r prime cubed here. So there's another formula, and like I said, we're just going to use this one for this problem, but you can also try and use this formula if you like. All right, so we'll need r prime and r double prime. Let's put that in white here. So r prime of t is going to be, all right, these are just polynomials, so the derivatives should be kind of easy. 1, 2t, 3t squared. Easier to see too. And then r double prime, take the derivative again, and we get 0, 2, and 6t. All right, now I need their cross product, and that's going to give me, remember how cross products work? This one times this one minus this one times this one is our first coordinate. So we have 6 times 2 is 12t squared minus 3 times 2t squared. So 6t squared there. All right, comma, 3t squared times 0, so 0, minus 1 times 6t. So we have minus 6t right there. And our last coordinate is going to be 1 times 2 is 2 minus 0 times 2t. So just 2. And then we can rewrite this as 6t squared minus 6t and 2. All right, and then we'll need the norm of this vector and the norm of this vector r prime. So if we go ahead and compute those, we have norm of r prime cross r double prime is square root of 36t to the fourth plus 36t squared plus 4. All right, and then norm of r prime is going to be square root of 1 plus 4t squared plus 9t to the fourth. And then I'm going to go ahead and cube this, because that's what we'll need. And if I want the curvature, I take these two things and I divide them. So I have, let's see, can I factor anything out? These terms all have a 4 common to them. Otherwise, I'm not sure I can simplify much. So we have 2 square root of 9t to the fourth plus 9t squared plus 1 divide by square root of 9t to the fourth power plus 4t squared plus 1. And that's about all I can think of to simplify this. Maybe you could put the roots together into one root if you wanted. I don't care that much. All right, and now we need kappa at 0. By the way, yes, this letter that I'm writing is the Greek K. It's called kappa. Kappa. That's how it's pronounced. Okay. So now kappa of 0 means just plug in 0 for all of your t's here, here, and here. And we should get 2 times the square root of 0 plus 0 plus 1 over square root of 0 plus 0 plus 1, which gives us 2 as the curvature. So the radius of an osculating circle to the twisted cubic at 0 is 2. That is what we should get if we draw a picture of the osculating circle. Okay, so that's our first examples video. I'll continue with examples 5 through 8 in the next video, where we'll do a little bit more computation with tangent, normal, and binormal vectors.